This is video number 2 for sections 7.4 and 7.5 using the completing the square method. Let's take a look at this sample problem. Find the x-intercepts of this function shown below. This is a quadratic function in standard form. We know it's a parabola. There's lots of things we could figure out about it. We are being asked to find x-intercepts. You always find the x-intercepts of a function the same way, and that is by setting the y equal to 0 and then solving for x. In other words, I need to solve this quadratic equation. Well, this is the one we looked at in the last video. Factoring method is no good because this thing is prime. Square root method is no good because there's two x's showing. So the only other method we have at the moment is this completing the square method. You have to follow a pretty specific set of steps in order to use the completing the square method. I've listed them for you here in this box, and so let me go ahead and demo. Step 1. You have to make the equation look exactly like this. Now, all this is trying to say is all of the terms with an x need to be on the left. Anybody who doesn't have an x needs to be on the right. And there cannot be a coefficient in front of the x squared. I'm pretty close to that right here. I think the only thing that I need to do is move this 4 over to the other side. Let's write down what we have. You'll notice I did something a little different. I left an empty space here. I did that purposely because I know what's coming, and I'll explain that in just a second. But I have now accomplished step 1. This equation fits this pattern exactly. The reason why you have to have only an x squared at the front here is those patterns we were looking at in the last video. They only work, you can check back on your handout, but they only work if there's just an x squared sitting here at the front. Okay, once you make the equation look like this, you can go to step 2. Step 2 is the step where you go ahead and you complete the square. So you're going to use that trick, that process that we learned in the last video. You're trying to create right here a perfect square trinomial, and we learned that that's pretty easy to do. You take the number in front of the x, I'm doing some scratch work here on the side, you cut it in half, -5, and you square that. -5 times -5 is 25. So you use that trick. Well, that's the magic number that needs to be inserted here in that space to create that perfect square trinomial. Now here's the thing. In the last video we were just playing with expressions, but now we have an actual equation. You can't just add random numbers into one side of the equation. You would change the equation. The only way you can do it is if you, as it says over here, add the same thing to both sides. You are allowed to add, just like we added 4 to both sides. Now what I'm doing is I'm adding 25 to both sides. I picked 25 because of that complete the square trick. Okay, you say, I don't know, it seems like we're making it worse. Only for a second, because now we get to step 3. Step 3 says, now that you created that perfect square trinomial, you know you can factor it in such a way that there's only one x showing. And what we said was it always is the same. It's an x followed by the cut in half number. The cut in half number was -5 squared. If you're in doubt, you could go off on the side and FOIL this and convince yourself that you're actually getting that answer. The right side is now 29. From this moment on, we know what to do because now we have turned this equation into something that only has one x showing. And if it has one x showing, we can use the square root method. How are we going to finish this off? Well, we already have the base and power isolated over here on the left, so I think we can immediately go to the square root step. Square root, don't forget the plus or minus. And then on the left, I have just x minus 5. On the right, I would simplify that square root if I could, but there are no perfect squares that go into 29, so I'm stuck. And I finish it off by simply adding 5 to both sides. And so we get, as our final answers 5 plus or minus the square root of 29. Remember, that represents two different answers. Now, we were looking for x-intercepts, so normally we write those things as ordered pairs. You would just have to pay attention to the instructions as to whether they want the exact answers or whether they want decimal approximations. If you want approximations, you'd have to go to the calculator, and there'd be two, right? 5 plus root 29 and 5 minus root 29. Let me grab those values off the calculator. So I got 10.4 and negative 0.4. If I wanted to write those as ordered pairs, that would be 10.4 comma 0. X-intercepts always have a y value of 0. And negative 0.4 comma 0. Here are the two final answers, at least in the approximate version. Okay, let's try that process again in this second example here. This time I didn't use a quadratic function or talk about x-intercepts. I'm just saying, here's an equation, solve for x. We are going to find any real or complex solutions here. Well, I can see it's a quadratic equation, and I can tell you that if you tried the factoring method or the square root method, that those will not work. And so let's just go ahead and go for the completing the square method. Step one, I got to put the equation in that special format, which means all your terms with an x on the left and all your terms without an x on the right. It's the 4x that's in the wrong place this time. And so that gives me x squared minus 4x. I'm going to leave that whole there, equals negative 16. I leave the whole because I know what's coming is that complete the square step. Okay, we're ready to do that now. Scratch work on the side, take the coefficient of the x, cut it in half would be negative 2, square it would be positive 4. That's the magic number that needs to be filled in here. If I add it to the left, I have to also add it to the right side of the equation to maintain the balance of the equation. Why did I do such a thing? Because guaranteed now, this thing on the left will factor in such a way that there's only one x showing. It's the x, it's the cut in half number, which is the minus 2, and then squared. The right, just work out the numbers, I get negative 12. And once again, this thing is now in a format where there's only one x showing, and so now I can use the square root method. I'm ready to square root each side. Square root, plus or minus. I can see I've got a problem here. I've got square root of negative 12. If they had only wanted real solutions, then I'd just stop right here and say, forget it, there are no real solutions. But since they said complex, I can just do the I thing to get final answers to this. Let's see, so far I have just x minus 2 on the left, and I have this square root on the right. Let's think, though, about how we can simplify that square root. Let's see, the negative is going to come out as an I, and then the 12, I can break that down into a 4 and a 3. So essentially I'm breaking it up into three pieces. The negative 1, which comes out as an I, the 4, which is a perfect square, and the 3, which is going to be left behind. So I believe that's going to give me, on the right side here, let's see, a 2, don't forget the plus or minus at the front of this thing, a 2 and an I came out from these two guys, and then the 3 got left behind. The plus or minus is just a reminder that there are two answers there. To finish it off, just add this 2 to both sides, and I believe I'm done. Here are the two final complex solutions. X equals 2 plus or minus 2I root 3. Make sure you put that plus or minus right at the first place where you take square roots, because it just stays there in front of the square root, or even in front of all of the pieces that came from the square root for the entire problem. Okay, so we've done a couple of examples, but here's what you need to know about the completing the square method. It's a pretty lousy method, okay? Because unless you have pretty simple examples like the couple that I've demonstrated, it gets really, really messy really fast. Take a look at this third example. I'm not even going to work it all the way. I just want to show you some of what starts to happen. If I wanted to use the complete the square method on this, of course, I'd have to move the 1 to the other side. But then I'm still not in the right format because I can't have any coefficient here in front of the x squared. The only way I can get rid of it would be to divide everybody by 3. And so here's what I'd now have. This is in the right format now, but it's just so messy to deal with because if I wanted to do the complete the square trick, I'd have to take negative 2/3. I'd have to figure out what half of that is. I'd have to square it. It's going to be some awful fraction that I'm adding into these places. And as a result, it's just a big mess. It's possible to do. It's just so messy that typically people don't do it. You say, well, what are we going to do then? Well, once you come up with a method that works every time, you start thinking, hey, if this works every single time, certainly there's some kind of formula we could come up with to take the place of having to run through these steps. And that's exactly where we're going to head next, is developing a formula for our fourth and final method. When you're doing the homework, I only gave you completing the square problems that are pretty reasonable to do. Because as I said, you reach a point where it just doesn't make any sense and you should just go to the formula.